Hi everyone, Mr. King here. We're going to go over another box volume problem. This particular box volume problem has equal size squares cut out from the corners of the piece of cardboard. However, these squares have unknown dimension. So we're going to make a little picture here to visualize things. And this is just a flat piece of cardboard. And since we don't know the cutout sizes, we do know they're squares, we're going to call that length x. In fact, in part B over here, we see that we are directed to talk about x representing the side length of each cutout square. So that's a given piece of information. Now, it's important to know what some of the other dimensions are. And in this case, it's a 15-inch length right there, and over here we've got a 25-inch length. Now that's not the width and length for the box, because to make the box we of course need to cut out the corners. Once we cut out these corners, we can see that we can fold up lengthwise like this, and we can fold up on the sides like this, and then we can make an open top box. And so that leads to some key dimensions that we should label on our picture. And one of those dimensions is this right here. That distance is 15 minus 2x. Why 2x? Because we had to cut out these two corners, so 2x comes out of the 15. Similarly, we have this distance, and it is 25 minus 2x right there. So we can now build a volume function with our picture, with the information in our picture. And it looks like this. V of x. We can get the pen to work here. Let's try that again. V of x is equal to x, the height of the box, times the 25 minus 2x, that could be the length of the box, and then 15 minus 2x, that's the width of the box. And there's our volume function. We actually don't need to expand this. Expanding that volume function actually will make extra work for us. So let's move on to the restrictions on x. Well, the restrictions on x, one of them is kind of common sense. We know that x must be greater than 0. If we don't actually cut out squares, we won't have a box. But the other restrictions come from realizing that our two lengths, 15 minus 2x, and then the other length, 25 minus 2x, these two lengths must, of course, be greater than 0. So let's see what happens when we make that condition as an inequality. Well, this leads to 2x needing to be less than 25, so x needs to be less than, well, 25 over 2 is 12.5. And similarly, 15 minus 2x must be greater than 0, and that leads to x needing to be less than 7.5. Well, which one of these conditions wins out? Well, if x must be less than 12.5, x must be less than 7.5, then clearly this one can be dropped. And so we see that x must be greater than 0 while simultaneously being less than 7.5. So the restrictions can be written in a compact form. And that compact form is a compound inequality. 0 with x in the middle, 7.5 on the right end. So 0 less than x, less than 7.5. Those are our restrictions on x. Now the next part of our analysis is to graph this. We're going to graph on our calculators, or as I will on TI Inspire on my software. So here's the box volume function, y equals x times 25 minus 2x times 15 minus 2x. It's graphed in a nice window that shows what we're interested in. This is primarily a quadrant 1 graph. And we go from x being 0 all the way over to x being less than 8 here. That must be 7.5 in fact, because of this restriction. 7.5 would be a 0, this volume function. So this whole region in between here is what we're interested in for our analysis. We can see that the volume seems to peak over here, and we're not quite sure what x value is going to get us to that point, and we will probably be trying to figure that out. So in this next screen, I have taken the liberty to do everything in terms of calculations with the calculator, with the grapher, that I will need to answer the rest of the questions in this practice sheet. So the first question we want to answer is, what is the x value that gives the maximum volume, and what is that volume? And that point is right up here. So we can see that the value 3.034, 3.03 to the nearest hundredth, with a volume of 513.05, that's where the maximum is, and that's the maximum volume. Remember, that volume is cubic inches. We have units in this word problem. So we can answer this question now about our maximum volume, and we'll just write it in here. The x value, if I get the pen to work, the x value is 3.03, and that's inches, and the volume at 3.03 inches, this is how we use function notation right here, is 513.05, and cubic inches can be written as inches cubed, like that. We have a few more questions to answer now in part F. And we're going to be finding x values or intervals of x values to answer these questions. Part 1 here is to find out what value of x will give us 200 cubic inch boxes. So we need to return to the graph to figure this out. So to figure out where the box has 200 cubic inches of volume, we graph a 200 cubic inch volume line. This is shown here as f of 2 of x is 200. And that goes across down here, and it intersects at 0.61, 200, and at 6.22, approximately 200. There are clearly two x values that give that same volume, and so we're going to write those answers down. So we have the answers 0.61 and 6.22 inches now to answer the first question here. Now the second question is, what is the x value, or x values, we should say, to give us less than 350 cubic inches? This is an inequality. We're going to need an interval to answer this question. The technique is going to be the same for the most part. We go back to the graph now. So in our graph, we also need to graph a horizontal line that represents 350 cubic inches. And that line is right here. The software, for some reason, seems to have found 349.9 instead of 350. I probably should have checked that ahead of time, but this is going to be close enough for our purposes here, since I'm just trying to show you how this works. But that line should be at 350. Anyway, we intersect that line with the volume function, which is the cubic. And this is one of the intersections. It's 1.241. Here's the other, 5.199. That's about 1.24 and 5.20 if we round to the nearest hundredth. And in this case, we want to know what x values give us less than 350 cubic inches. We've got to be careful here. That's where the volume equals 350. It's less when the blue line, the volume function, is below the 350 line, which is horizontal. And that occurs for these x values, so that's x greater than 0 up to 1.24, and then from 5.20 all the way over to the maximum x value we can have, which is just less than 7.5. We have to give two intervals for our answer. And so we've got two intervals to write down here to answer part 2, and we need to let x go from 0, but not equal to 0, to 1.24, and that's in union with a second interval, 5.20 inches to 7.5, and not including 7.5. And again, the units are inches for these x values. So those are the x values that give us a box with less than 350 cubic inches. Finally, the other type of question we might see is the one like in part 3. What values of x will give greater than or equal to 500 cubic inches? And for one last time, we will go back to the graph and we'll see how we can get the answers for this one. Again, we graph a volume line that's at 500 cubic inches. We intersect it with the blue volume curve again. These intersections are at 2.5, 500, and about 3.60, 500. Now we want the volume to be greater than or equal to 500. Well, that only occurs when the volume graph is above the line at 500, the horizontal line. So this will be an interval that goes from 2.5 to 3.596 or 3.60. We'll write that down now, and then I think we'll be done with this problem. So our final answer is to say that the volume is greater than or equal to 500 cubic inches when x is on the interval from 2.50 to 3.60. And here I'm assuming that the 2.50 is correct because I didn't see any additional decimals in my graphing software. So hopefully that is in fact correct. The process is correct. So we've answered all the questions to this box volume problem now. It's a little bit more complicated possibly than the ones we did earlier in this chapter, but it's quite similar as well. I hope this tutorial helped you out. This is King Pre-Calc over and out.